Hello, this video goes through the mechanics specimen paper for Edexcel. This is a first year paper, so AS paper. So the first question we've got is a small ball is projected vertically upwards from point A, which is 19.6 meters above the ground. The ball strikes the ground for the first time 4 seconds later. The motion of the ball is modelled as that of a particle moving freely under gravity. Use the model to find the speed of the ball as it hits the ground for the first time. So for this question, we want to always try and draw out the situation. So a small ball is projected vertically upwards from a point A. So we'll take point A and the ball goes vertically upwards and it's 19.6 meters away from the ground. So this is 19.6 meters. And the ball strikes the ground for the first time 4 seconds later. So the path of the ball is to go up and then straight back down again and hitting the ground. And this motion of it going up and down is going to take t equals 4 seconds. So from here we can then make some determinants. So we want to use the model to find the speed of the ball as it hits the ground. So we're going to use SUVAT, so S-U-V-A-T. The motion of the ball is modelled as that of a particle moving freely under gravity. That means acceleration is equal to g. Now here you've got to make a decision. Do you take upwards as positive or do you take downwards as positive? And you can take either way, it doesn't matter. Because we're not interested in, we don't know anything about the velocity, the initial velocity, it might be a good idea to take downward as positive, but I'll show both examples just in case whichever way you took it. So the first way I'm going to do it is take upwards as positive. So we're taking up as positive, and therefore S is going to be negative 19.6 meters. U is equal to, we don't know. And in this one, we don't care because it's finding the speed of the ball as it hits the ground. Velocity is what I'm interested in. Acceleration is minus 9.8, and time is equal to 4. From here, I'm going to use my SUVAT equations. So to remind you, the SUVAT equations is v squared equals u squared plus 2as. S equals ut plus half at squared. V equals u plus at. And v equals u plus S equals u plus v over 2 times t. Here we're not interested in u. So this one's an interesting one because we're not going to use this one. We're going to use the one that is not often talked about, and that is S equals Vt minus half At squared. So it's kind of the forgotten one, the forgotten equation necessarily. It's not, but it is a possible one that you could get. So here what we could do is then just plug in the numbers. So S is minus 19.6, V we don't know. So it would just be V times 4 minus a half times minus 9.8 times 4 squared. From here we just sort out our equation so it makes it look a bit nicer. So that's 4V minus a half times 9.8 times 16. On the calculator is going to be minus 0.5 times minus 9.8 times 4 squared is equal to 78.4. So we're going to subtract that over to the other side, minus 19.6 minus 78.4, and then that's equal to 4V. So then this just ends up being minus 19.6 minus 78.4, which is minus 98. So minus 98 equals 4V. So V is equal to minus 24.5 meters per second. It asks for the speed, so therefore we can ignore any signs in this case. So we can just say V is equal to 24.5 meters per second. Again, to show you the numbers, if you did it the other way, so if you did as downwards as positive, this time you would have S equals 19.6. U, you don't know and you don't care for this question. V is a question mark. A this time will be positive because we're going down, and T equals 4. And again, you would use the same numbers, the same equation. This time instead of a negatives, you would get a positive answer of v is 24.5. Question 2. The ball rebounds from the ground with a vertical speed of 14.7 and next comes to instantaneous rest at the point B. Use the model to find the height of B above the ground. So this question, you've got a flat ground and the ball has rebounded upwards at a speed of 14.7. So here we just take a new situation and we say the initial speed 14.7 and it will reach a point B. And you want to find what B is. So at this point here, V, the final one, is instantaneous rest. So we can say that the final velocity is equal to 0. So, and this time we're going to take upwards as positive because our initial speed is going up. So we take upwards as positive. So it's always good to define which direction you take early on. So that means you don't mess up your signs in your subat. So S is what I'm interested in. U is 14.7. V is 0. A is minus 9.8 because the gravity is the only force acting on it, and time we don't know and we don't care. Going to equations, you're looking for the equation that does not have time, and that is v squared equals u squared plus 2as. So we use our equation, v squared equals u squared plus 2as. So we get 0 squared equals 14.7 squared plus 2 times minus 9.8s. And then you can just plug in the number, rearrange, so it's going to be 0 squared minus 14.7 squared equals 2 times minus 9.8, which is minus 19.6 s. And then this just ends up being minus 14.7 squared, which is just minus 216.09, divided by minus 19.6 is equal to s. Plugging that into the calculator, you get a final value of s is equal to 11.025 meters. So around 11 meters is what we will get. Again, a good way to do is look how many significant figures you have. So here, 3 significant figures is probably suitable. So 11.0 or 11 meters is fine. But you could also leave the full answer. The final part for question 1 is in a refined model of the motion of the ball. The effect of air resistance is included, and this refined model is now used to find the speed of the ball as it hits the ground for the first time. How would this value of the speed of the ball as it hits the ground for the first time compare with the value found in part A? So here, if we think about what's happening with the ball is still travelling downwards with gravity, but now has air resistance acting against it, which means that the force on the ball is reduced going downwards because you have this opposite force that goes against it. Therefore, the total acceleration of the ball would reduce because now you've got an opposing force. So again, this comes into the idea that F equals ma, where the net force, well, before in the initial one, so in part A, you just had gravity, and now you've got an additional force. So the net force is now gravity minus air resistance. So it's going to be lower. So therefore, total acceleration of the ball would reduce, and therefore you would find that the new value would be lower. Again, you don't need to put such detail for this one. It's a 1-mark answer, so new value would be lower. But here we're just going to explain why. And that brings to the end question 1. Question 2. A car travels along a straight horizontal road between 2 sets of traffic lights. The distance between the 2 sets of lights is 1,500 meters. So again, that's useful to know. So we know that S equals 1,500. In the model of a journey, the car leaves the first set of traffic lights accelerating uniformly from rest. So again, we can say U equals 0 until it reaches a speed of v. So the final velocity is v. Then immediately decelerates uniformly until it comes to rest at the second set of traffic lights. The car completes the journey between the 2 sets of lights in 120 seconds. So we know that t equals 120, and we actually know that the final speed here is going to be 0, so not necessarily correct here. First of all, sketch a velocity time graph which represents the above model of a journey of the car between the 2 sets of lights. So he wants a velocity time graph. So again, we draw the axes here, and we are going to then, so the first step we want is velocity time, so v against t. We know that it will take 120 seconds to complete, and it tells us that in the model the car uniformly accelerates from rest until it reaches a speed v. So we know that it uniformly, and we don't know what v is, so we're just guessing at this point, and we don't know what t is either. So we're just going to guess, and we're going to say that this is going to be our big V, and then immediately decelerates uniformly until it comes to the second set. So it's going to decelerate here very quickly and come back down. So you end up with a triangle as your final velocity time graph. Using the model, find the value of V. So to use the model here, what do we know? So we know that the area of the graph represents the distance travelled, because that is the one of the key components of velocity time graph. So area under graph equals distance travelled. So here, when we look at the area here, it's going to be half times base times height, because it's the area of the triangle. So it's going to be a half. This is a base is 120, and the height is this value here. So from top to the height, that's equal to v, and that's equal to the total distance, which is 1,500. All we do here is then rearrange. So v is equal to 1,500 divided by a half times 120, which if you plug into your calculator gives you a value of 25. So v is equal to 25 meters per second. Part C, it explains why there is a range of possible values of t which satisfy the requirements of the model. So here it's given that the car accelerates for t seconds, so it accelerates uniformly for t seconds. There's a range of possible values for t which satisfy the requirement. This is primarily because the area of the triangle does not depend upon t. Okay, the only thing it depends upon is the total time, which is 120 seconds, and also the velocity. It doesn't matter if, for example, it accelerates really quickly and then comes back slowly, as long as the area remains the same. T doesn't matter. It doesn't matter how hard it accelerates. So therefore, t can take any value which is between the total time. So it can be obviously not exactly 0, but t, it can be between 0 and 150 seconds. And this is because, again, the area of the triangle only depends upon the final time, not anything to do with what's happening in between. It can do anything in between. It can accelerate, decelerate, etc., etc. As long as the area remains the same, it doesn't matter. So t can go between 0 and, oh, not 150, sorry, 120 seconds, which is the total time taken. So just one improvement. So one improvement that we could have, one main improvement, is that cars don't just suddenly accelerate and then decelerate. There's usually a time period in between. So we could have variable acceleration and deceleration. So for example, how would that look like? Well, that would look like a curve, which is a more accurate of what's happening in terms of accelerating and decelerating. And also this is suggesting that the car suddenly is accelerating and then suddenly decelerates at the same amount. Obviously in real life you wouldn't, your acceleration would be varying, so your velocity time graph would be more of a curve than a perfectly straight line. And that brings in question 2. Question 3. A ball of mass 0.4 kilograms rests on a rough horizontal table and is attached to one end of a thin rope over a pulley which is a ball of mass 0.4 kilograms rests on a table, so this is 0.4, so we can start to, again, when you see this, start to draw out what you know. So this is going to be 0.4, so this is weight, which is P, attached to one of a thin rope. The rope passes over a pulley which is fixed to the table. The other end of the rope is attached to another ball Q of mass M. So this one is going to be weight is equal to, so W equals mg, so the force on the ball is going to be 0.4 g. We know that it's a rough surface, so there's going to be friction that acts against the motion because the tension of the rope is pulling the ball to the right, so the friction is going to try and hold that. Then on the right hand side we have tension of the rope on the ball that's pulling it upwards, and then we also have the weight, which we don't know at this stage. The system is released from rest with a rope and with Q at a height of 2 meters above the ground, and Q moves downwards with an acceleration of 2.5 meters per second. So here we know that at this point S is equal to 2, U is equal to 0 because it's starting from rest, V I don't know, acceleration is equal to gravity because we're going to take downwards as positive because we're moving 2 meters downwards, so acceleration is not equal to gravity, acceleration is equal to 2.5 meters per second, as it states in the question. In the subsequent motion, P does not reach the pulley before Q reaches the ground. So Q reaches the ground first and then P reaches the puddle. The balls are modelled as particles, the rope is a light inextensible string, and the pulley is being small and smooth. So these are general modelling assumptions. The total motion to the motion of P is labelled as having a constant magnitude of 1.5. So this means that the friction is equal to 1.5 newtons, and the acceleration due to gravity is modelled as 10 meters per second, which means that for the whole situation G is equal to 10. So using this model, find the two significant figures, the tension in the rope. So if we look at what's happening here, so for ball P, going to the left is going to be 1.5 newtons, and going to the right is equal to tension. And that's equal, so the net force that we're going to have is T minus 1.5. And then we know that F is equal to MA, or F net. So here the force is the tension going to the right minus the friction which is going to the left, is equal to the mass, which is 0.4, times the acceleration A. But we know that the ball, if Q accelerates downwards at 2.5, we know that P must accelerate at the same time because they're connected together. So we can say that T is equal to 2, that A is equal to 2.5. So therefore we can say that T equals 0.4 times 2.5, which is 1. So 1 plus 1.5 is equal to T, so T is equal to 2.5 newtons. And then the next question what's to find is the value of M. So here, if we look at what's happening at Q now, at this ball, we have the weight that is going downwards, and we've got the tension that is going upwards. The ball is going down, so the net force is equal to W minus tension. And we know that the F net is equal to MA, so the weight minus tension is equal to the mass, which is big M, times A, which is 2.5. The weight of this is equal to mg, so that's going to be m, because we don't know the mass of q, times 10 minus t is equal to 2.5 m. So put in the values that we know, which is 10 m. The tension we've already found from this one, so the tension on both balls is the same due to the rope, so the tension is 2.5. So it's 10 m minus 2.5 equals 2.5 m. And then we just rearrange, so 10m minus 2.5m equals 2.5, 7.5m equals 2.5, so So therefore m is equal to 2.5 divided by 7.5, which is equal to a third. So m is equal to a third kilograms. Find the time after release for Q to hit the ground. Use the model to find the two significant figures. So also do read the question. So to two significant figures, this is equal to 0.33 kilograms. Okay, the time after release for Q to hit the ground. So again, we've already set up most of our equation. So we want to find the time it takes to hit the ground. So here we're going to borrow most of this one. So Q travels 2 meters to hit the ground. It starts from rest. The velocity, I don't know. Acceleration is 2.5. And our time, I want to know. So we're going to use the equation. If we go back to our SUVAT questions that we had, we're looking for one that does not have velocity, which is going to be, we need to find time, so it's going to be S equals ut plus half at squared. So S equals ut plus half at squared, because it doesn't have the final velocity. And then we can plug in our numbers. So we've got 2 equals 0t plus a half times 2.5 t squared. So 2 equals 1.25 t squared. So t is equal to 2 over 1.25 square rooted. Plugging that into our calculator, we get a value of 1.2649 seconds, which to two significant figures is equal to 1.3 seconds. State one limitation of the model which will affect the accuracy. So basically the limitations are all mentioned here. Probably the main one is that the pulley might not be smooth. Which would affect your answer, because you're including, if the pulley is not smooth, then you've got to think about the resistance of the pulley. So that's why we consider the pulley smooth, because then we don't have to worry about any extra resistance due to the pulley, like friction. But of course in real life, the pulley might have some resistance. You might also have things such as the strings have mass, and also that the strings can be extended as well as the fact that the balls might not be modelled as dot particles, but also have volume as well. Okay, the last question we have is the particle P moves along a straight line such that time is equal to, time at t seconds is t is greater than or equal to 0 at a velocity of v, and it's given as v equals 16 minus 3t squared. Find the distance travelled by P in the first second. So these questions, you need to remember that S, V, T, where S is distance or displacement, V is velocity or speed, and T is time. Not time, sorry, it should be SVA. And to go between them, we differentiate to go down, and we integrate to go up. So here, when you've got V equals 16 minus 3t squared, if you want to find the distance, you're going to have to integrate this. So 16 minus 3t squared, and this is because if we have S, then V is equal to ds dt, and A is equal to dv dt, which is equal to d2s dt squared. So if we integrate V and we integrate 16 minus 3t squared with respect to t, we're going to get our value. So S is equal to 16t minus 3t cubed over 3, and then remember that you must have a plus c as well. But also we want to find the distance travelled in the first second, so actually this is going to be slightly incorrect, and this is because we know what the time will be, it's in the first second. So actually in this question we're going to put limits onto our answer, so therefore we can rub this out, and we can solve it as a definite integral, where S is equal to 16t minus 3t cubed over 3 between 1 and 0. Tidying that up slightly, is just going to be 16t minus t cubed between 1 and 0, and then plugging in the numbers is equal to 16 times 1 minus 1 cubed, subtract 0 minus 0. And then plugging that in, we're going to get an answer of 15 meters as our final value. The next step we have is the value of t at the instant when p changes its direction of motion. So if it changes its direction of motion, that means that v is equal to 0 because it's stopping and then going backwards. So when v equals 0, 0 is equal to 16 minus 3t squared. From here we can then just rearrange and solve. So 3t squared is equal to 16, t squared is equal to 16 over 3, and then t is equal to the square root of 16 over 3. Usually you would put a plus or minus, but since we're dealing with time, you can't have negative time. So your value for t is 4 root 3 over 3, which is 2.31 seconds to 3 significant figures. The last one we have is the value of t at the instant when p returns to its starting point. So when it returns to its starting point, we are going to look at s. So for this one here, we're going to say that s is equal to 16t minus t cubed. And we are then going to say that, well, the value of t when the instant p returns to a starting point, so s is equal to 0, because it's returned back to the start, so 0 equals 16t minus t cubed. From here, we can say, take out a factor of t, so t squared, we can actually, one thing to do is to rearrange this equation, so we get t cubed minus 16t equals 0, so therefore we get the biggest power as a positive, and then take out a factor of t, so it's t squared minus 16 equals 0, which means that we get t equals 0, or t squared minus 16 equals 0, so t squared equals 16, so t is equal to the square root of 16, which is equal to 4. Again, you could argue put plus or minus, but time doesn't have can't be negative, so if we could say that t is equal to 4 seconds, and this is the value of when it returns back in, because t equals 0 was the initial starting point. So this is your final answer. And that brings to the end this paper.